Hello everybody, this is Ilija Barukcic, Jefa, Germany, October the 1st, 2017. I welcome you to my movie on logic, causation and probability theory. An intense discussion over thousands of years has cast doubts on the adequacy of any theory of an explicit definition of causation provided to us by many different authors. Philosophers still disagree even over the metaphysics of causation and whether there is causation at all. However, questions about the foundation of causation may be usefully divided into questions about the causal relation and questions about causal relata. What are the causal relata? Are the causal relata transcendent or are the causal relata immanent? Or both or none? Or what? This question is connected to the question whether causation is an absolute relation whose nature does not vary from one context to another. Has causation existed forever? Does it exist? Will it exist forever? Surprisingly enough, among many other positions, David Hume's meanwhile outdated understanding of causation is grounded more or less on a logical fallacy. According to David Hume, we may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second, or in other words, where if the first object had not been, the second never had existed. Essentially, causation, according to David Hume, can be reduced to the sentence an object followed by another. Once again, an object followed by another. Once again, an object followed by another. Example, a day is followed by the night. But because of this, there is no cause-effect relationship between a day and a night. The most of us will agree on this point. And this is the so-called post hoc ergo propter hoc fallacy, which is the foundation of David Hume's approach to causation. One consequence of David Hume's approach to causation is the last sentence as quoted above. David Hume says, if the first object had not been, the second never had existed. Once again, if the first object had not been, the second never had existed. Once again, if the first object had not been, the second never had existed, which is one of the first explicit definitions of causation in terms of counterfactuals. David Hume's account to the concept of causation may be rich in insights. Still, a variety of issues within and objections to David Hume's account to the concept of causation are meanwhile widely discussed in literature. At the end, David Hume's concept of causation has gained too much attention. David Hume's account of the concept of causation is called a regularity theory of causation, and as demonstrated before, is grounded on the post hoc ergo propter hoc logical fallacy. In this context, the known success of quantum mechanics, and to a lesser extent of some other theories, has shaken our faith in the deterministic relationship between cause and effect. The aim of this contribution is to characterize the relationship between cause and effect while using the tools of Boolean algebra and classical logic. The motivation for a classical logic-based approach to causation and the trial to characterize causation in terms of classical logic is the fact that classical logic, assumed as generally valid, may enable a closer match with a common sense judgment about causation and is at the end useful to recognize the basic of causation. In the following, let us analyze the relationship between cause and effect under conditions where there is only one single cause and only its own one single effect, and all this at a certain point in space-time t. Further, if a cause at a certain point in space-time t is given, is existent, was measured, etc., we denote this by the number +1. If a cause at a certain point in space-time t is not given, is not existent, was not measured, etc., we denote this by the number +0. Further, if an effect E at a certain point in space-time t is given, is existent, was measured, etc., we denote this by the number +1. If an effect E at a certain point in space-time is not given, is not existent, was not measured, etc., we denote this by the number 0. In the following, we will analyze the 4 basic Bernoulli trials to get some new insights concerning the relationship between cause and effect. The first is the so-called Bernoulli trial number 1. In general, causal claims are usually of the form event C caused event E. This situation is shown schematically in the following picture. At the Bernoulli trial t equal 1, we measured a cause C and we were able to measure an effect E. This is exactly what we understand under causation. A cause has an effect has a cause. Thus far, we are authorized to assume a cause-effect relationship. We obtain cause and effect equal 1. Still, even if this illustrates how it is and how it should be, it is not enough to rely our understanding of causation only on this measurement. This measurement demonstrates only the coincidence of cause and effect. If we would rely only on this measurement, we would commit the so-called cum hoc ergo propter hoc fallacy. In other words, events which occur together can but must not be caused by each other. Once again, events which occur together can but must not be caused by each other. According to the Bernoulli trial 1, a cause C has cause and effect E, which determines somehow a kind of an asymmetry of causation 2, since the effect E must not be the cause of the event C. Even if there are circumstances of a bidirectional or cyclic causation, many times the asymmetry of causation is linked to the claim that causes precede their effects in time, which is neither correct nor does it hold in general. Especially in probabilistic approaches to causation, causal relata are represented by events, for example, in a probability space. In fact, classical logic should help us to answer another basic aspect of the relationship between cause and effect. Thus far, let us regard the Bernoulli trial number 2. May an effect fail to occur in the presence of its own cause? May an effect fail to occur in the presence of its own cause? Once again. May an effect fail to occur in the presence of its own cause? At the Bernoulli trial t equal 2, we measure the cause, but we fail to measure an effect E. In other words, a cause was not able to produce an effect. Maybe at the Bernoulli trial t equal 2, the cause has just not yet acted or has ceased to act. However it may be, a cause as such is a cause only insofar as it produces its own effect. A cause is determined by nothing else than to have an effect. Consequently, a cause insofar as it has not yet acted, or if a cause has ceased to act, then it is not a cause, it is something else. In this context, it is valuable to recall Hegel's account on causation. The 19th century German philosopher Hegel provided a very abstract and idealistic philosophical account of the nature of causality while relying on the dialectical method. According to Hegel, therefore, though the cause has an effect and is at the same time itself effect, and the effect not only has a cause but is also itself cause, yet the effect which the cause has and the effect which the cause is are different, as are also the cause which the effect has and the cause which the effect is. Thus far, cause and effect, however much they may be postulated as being isolated from each other, both are equally meaningless one without the other. Hegel demands, thus, in the causal relation, cause and effect are inseparable. A cause which had no effect would not be a cause, just as an effect which had no cause would no longer be an effect. And rightly too, a cause which had no effect would not be a cause, just as an effect which had no cause would no longer be an effect. Once again, a cause which had no effect would not be a cause, just as an effect which had no cause would no longer be an effect. Nonetheless, any approach to causation should entirely be able to answer the question, may an effect still occur in the absence of a cause? Once again, may an effect still occur in the absence of a cause? Once again, may an effect still occur in the absence of a cause? Once again, may an effect still occur in the absence of a cause? At this moment, we should remember that we are analyzing the relationship between cause and effect under conditions where we have only one cause and one effect, not a lot of causes and a lot of effects. This is another experimental setup. We are now under conditions where we have only one cause and one effect, and the question is, may an effect still occur in the absence of a cause? At the Bernoulli trial t equal 3, we observed no cause, but we were able to measure an effect. In other words, an effect can occur without a cause. Well, if an effect can occur without a cause, then a causeless change would be possible. In this context, we don't need causation at all. Already because of formal aspects, we cannot accept a cause-effect relationship as given due to Bernoulli trial equals 3. General claims such that an effect can occur without a cause abandon a deterministic relationship between cause and effect in principle. At the Bernoulli trial T equals 3, an effect E had no cause C. In general, an effect which had no cause is no longer an effect, but something else. At the Bernoulli trial equals 3, we cannot accept a cause-effect relationship as given. Causal relationships are normally objective features of reality. For purposes of definiteness, an effect insofar as its cause has vanished is no longer effect. The discussion of the previous section conveys some of the complexity of the problem of inferring causal relationships from measurement. Under conditions where we have only one cause and one effect, the problems are limited. But as soon as we are under conditions of multi-causality, of many causes, many effects, the problems are solvable but must be treated in another way. Indeed, causal claims are usually of the form event C caused event E, imply equally that if event C had not occurred, event E would not have occurred too. Once again, if event C had not occurred, event E would not have occurred too. At the Bernoulli trial T equals 4, this situation is described in detail. Bernoulli trial number 4 is a demonstration of the basic idea of counterfactuals or of counterfactual theories of causation. However, even if singular causal claims in terms of counterfactual theories of causation have become popular in the last 40 years, doubts on the adequacy of analysis of singular causation in terms of counterfactuals still remain. Here is an example. Let us assume that smoking is a cause of human lung cancer. Further, for the sake of the argument, let it be true that Mr. David Lewis has smoked and that Mr. David Lewis has developed lung cancer. Thus far, according to the principles of causation in terms of counterfactuals, it is true that if Mr. David Lewis had not smoked, he would not have developed lung cancer. But it is equally true that if Mr. David Lewis had not been born, he would not have developed lung cancer too. Consequently, according to the counterfactual theory of causation, not being born is a cause of human lung cancer. Once again, not being born is a cause of human lung cancer. The question, of course, is how can Mr. David Lewis develop lung cancer if Mr. David Lewis is not born at all? According to the counterfactual theories of causation, this is possible. Counterfactual theories of causation are producing too many absurd results and are completely useless on this special account. There have been a number of attempts to revise the counterfactual theories of causation and so to avoid these and similar problems, but without definitive success. It is not appropriate to reduce the relationship between cause and effect or causation as such only to one single aspect, for example like the situation in Bernoulli trial 4. A theory of deterministic causation must be able to deal with all 4 Bernoulli trials as demonstrated in this movie. Thank you very much for looking this movie. Have a nice day. Bye bye. Thank you very much. Bye bye. Bye bye. Thank you very much. Bye bye. Bye bye. Thank you very much. Bye bye. Bye bye. Thank you very much